Hello dears, this session is dedicated to NCERT discussion of the very fundamental mole concept. As I say very often, mole is the gateway to all physical chemistry chapters. If you have this chapter correct, you have every chapter a possibility. What does that mean? It means that there is a possibility that you would be able to master all the remaining chapters of physical chemistry, but if you mess up with this chapter, if you are lethargic, if you have not practiced well, then my dears, in general, every chapter of physical chemistry, you would find problem solving very, very difficult. You might enjoy the theory teaching by the teacher, but when you start solving problems on your own, without a good mastery on mole concept, you will find it always difficult. In order to make sure that you don't face this difficulty, there I am presenting to you the solutions to NCERT chemistry of standard 11th and unit 1, some basic concepts of chemistry. Let's begin. Without wasting time, let's take a look at the first question. Calculate the molar mass of the following. Well, what is molar mass? Molar mass means mass of 1 mole, and if you have molecules, mass of 1 mole of molecules. How do we do? We add molar masses of atoms so that we get molar masses of molecules. That's very simple. So H2O. Now H2O has 1 hydrogen and 2 oxygens. No, sorry. What does H2O mean? It is not 1 hydrogen, 2 oxygens. It is 2 hydrogens, and if nothing is written, it is understood as 1. Like in mathematics, in algebra, if you have 1x, you just say x. You don't write down 1. In the same fashion in chemistry, while writing a chemical formula, a formula indicates how many atoms of which element are present. So if hydrogen element 2 atoms are present in a molecule, we write H2. Oxygen, only 1, we just write O. We don't write 1. We eat away that 1. It is understood, if nothing is written, at least 1 atom has to be there. Now, atomic mass of hydrogen is 1. And there are 2 atoms of hydrogens. Atomic mass of oxygen is 16, and there is 1 atom. If we just add up, you get how much? 18 grams per mole. This is the molar mass. Oh my God, how do you get that unit? 1 also, if you just solve it more with units, 1 gram per mole is atomic mass of hydrogen. And there are 2 hydrogen atoms. So total, so much. Oxygen, 16 grams per mole of oxygen atoms into 1. If you add up, you have 18 grams per mole of water molecule. This is molar mass of water. What about CO2? Please don't forget the units, correct units you must write. CO2. Carbon is 12 grams per mole, and there is 1 atom of carbon. If you look at CO2, it is C1O2. You have 1 atom. You have 2 atoms of oxygen. 1 atom is 16 grams per mole, and you have 2. If you just add up, you get 44 grams per mole. Wow, this is molar mass of carbon dioxide. Yes, indeed. What about methane? Lovely. 12 grams per mole of carbon into 1 plus 1 grams per mole of hydrogen into 4. That makes it 16 grams per mole. This is the molar mass of methane. Simple, isn't it? Calculate the mass percent of different elements present in sodium sulfate Na2SO4. Now, what is mass percent? I hope you understand percent, right? We get percentage marks in school exams also. Now, board exams for that matter. So all we need to do is, first we have to find out what is the mass of each element in sodium sulfate. Sodium sulfate, just let me write down, what all do I have? I have sodium, yes, then I have sulfur, and I have oxygen. Sodium, sulfur, oxygen. Fine. Number of atoms in a molecule, या formula unit. How many atoms of sodium are there? Na2. So 2 atoms of sodium, 1 atom of sulfur, and 4 atoms of oxygen. Atomic mass. Sodium is 23, sulfur is 32, oxygen is 16. Oh, how do you know this? I remember this. How do we get this? Eventually you will come to remember this, but you also have a table of atomic masses. From there you can see, and this is a data you have to get from there. Okay. Now, one atom of sodium is 23 units, AMU, right? Now, if I have two atoms, how much would that be? So, then you have mass of an element. If I want to calculate this, mass of a given element within one formula unit of sodium sulfate, what would that be? 2 into 23. One atom is 23 AMU. There are two atoms. What do? I multiply them. So I have 23 into 2, which is 46. 32 into 1, which is 32. And 16 into 4, which is 64. Fascinating. So if I just add them up, this comes out to be 142. Out of total 142 units, 46 units is the mass of sodium, 32 units is the mass of sulfur, and 64 units is the mass of oxygen. Can I calculate the percentage? Yes, I can. Percentage by mass is mass of any one thing divided by total mass, divided by total mass into 100. That is the formula. The percentage by mass of sodium is 46 by 142 into 100. 32 upon 142 into 100 is percentage by mass of sulfur, and percentage by mass of oxygen would be 64 by 142 into 100. Oh wow. And as I calculate, I get around 32.4% sodium, 22.5% sulfur, and 45.1% oxygen. You might say that I've calculated separately and given you the answer. Yes, because we needed an accurate answer. If you want to learn the tricks of calculation, although it's a part of mathematics, but it is very valuable in chemistry, I could give you some hint. How did I do the calculations? Rough, quick calculations. See, I remember that 1 by 7 is 0.1414. Okay? And 1 by 14 is 0.0707. This is one rough calculation I remember. Okay? Now, the moment I get 142, please note, I am just trying to teach you approximate quick calculations so that you can get, at least you can cross-check roughly, is this the correct answer or not. So, 1 by 14 is so much, fine. So, had I had 1 by 140, this would have been one more zero, right? And I have this multiplied by 100. So, if I have 100 by 140, it would be 0.7. It would be 0.707070, like this. But I have 142. That is what I'm saying. Take something close. This is something which I remembered. So now 142, the moment I take, if I increase the denominator a little, the numerator goes down a little. So instead of 0.707, I say approximately it will be 0.7. So roughly 100 upon 142 would come out to be approximately 0.7. So what I need to do, I have to multiply 46 by 0.7, which is a very easy calculation. 7 6 are 42, 7 4 are 28, 32. I get roughly approximately 32.2%. Accurately, it is 32.4%. I am very close, as you can see. Similarly, 32 by 142, which is, that would be 32 into 0.7 or 64 into 0.7. Approximate values also, if you want, you can get. But if you want more accurate, you have to do it, of course, more accurately. Done? Done. Determine the empirical formula of an oxide of iron which has 69.9% iron and 30.1% dioxygen by mass. Now, please remember, dioxygen actually is a molecule, not element. The word di has no significance. We are just worried about oxygen. This is the percentage of oxygen. Now, what is the meaning of empirical formula? Empirical formula just means that I will take the ratio of number of atoms present within a formula unit. Say for example, if it is FeXOY, that means number of atoms of Fe divided by number of atoms, Fe is iron, of oxygen. Please note, it is not O2, it is oxygen. That ratio comes out to be X upon Y, because iron, if iron is X, oxygen is Y. It just indicates the ratio, and the minimum integer ratio, if we use that, is called empirical formula. So I'm just supposed to find the number of atoms ratio, which is actually the ratio of number of moles of atoms also. Number of moles of, because mole also indicates a bigger number, but a number only. If I find out whatever is the number of moles of iron divided by number of moles of oxygen in a given sample, I get the empirical formula. Yes. Can I find number of moles? Of course I can. How? Let's see. We have mass. We have iron and oxygen. And let us say we have 100 grams of total iron oxide. That means what would be the mass of iron? 69.9 grams. And oxygen atom is 30.1 grams. This is the mass. Do we know the atomic masses? Table of atomic masses is given in NCERT. You have to consult that. Iron, normally we use 56, but NCERT specifies as 55.85. And unless you are very, very accurate, you will start getting wrong answers. So make sure that you use a very accurate value. It's a very dirty, ugly and cheap calculation. I hate it. But nonetheless, we have to do this. And what do you get? Moles is mass by atomic mass. Can I find this? Yes. It is 69.9 divided by 55.85. So many moles. And this is 30.1 divided by 32 moles. Oh my God. This is it? Yes, this is it. Can we calculate that? Of course we can. We are supposed to find the ratio. All we need to do is, now mathematically, we just have to solve. If one of them is X, the other one is Y, this ratio has to be X by Y. We just solve that. There's a very common error. Oxygen, O2, dioxygen mass is O2, then it is 32. If you're just using O atoms, it is 16 grams per mole. It has to be divided by 16, my dear, not 32. Yes. If you divide that, this would come out to be 1.25. You can happily calculate and see. And this comes out to be 1.88. Oh my God, what do I do? Take a ratio. And if you take a ratio, what do you get? Well, 1.25 by 1.88. If I would try for an integer ratio, well, that comes out to be, it's around 2 by 3. Okay, so it is Fe2O3. Yes, my dear, it comes out to be Fe2O3. What are the typical traps? One possibility of making error is you get the atomic mass wrong. Yes. The second possibility is, again, instead of 60, if you take 32, that also becomes ugly. Please remember, if you get 32, that means you're taking O2 here. So don't you forget to get an extra 2 in case you want to push that in. But that is not advisable. This is the best. And there we are. Calculate the amount of carbon dioxide that could be produced, okay, when 1 mole of carbon is burnt in air. That's very simple. C plus O2 gives CO2. Now, what does amount means? Amount means moles, volume, mass. Actually, it could be anything, but often it refers to mass. Okay, so let's try. If I have 1 mole carbon, and if it is totally burnt, it will give me 1 mole CO2. And molar mass of CO2, how much is that? Molar mass of CO2 is 44 grams per mole. Therefore, mass of CO2 is moles into molar mass, which is 44 into 1, which is 44 grams. So I would get 1 mole of CO2 or 44 grams of CO2. Right? Right. 1 mole of carbon is burnt in 16 grams of oxygen, dioxygen. Fine. If I have carbon 1 mole, and if I have O2, dioxygen, and I am told this is 16 grams. Now 16 grams of O2. Now mass of O2 is 16 grams. Therefore, moles of O2 is mass by molar mass, 16 by 32, and molar mass of oxygen, it's 32. So this comes out to be 0.5 moles. Oh, is it 0.5 moles alone? Yes, it's just 0.5 moles. And I'm getting CO2, of course I'm getting CO2. So initially, this is the reactant. Now, please note, O2 is no longer in excess, it is less. So, let us say how much can react. Maximum 0.5 can go, maximum 0.5 can go, and maximum 0.5 is formed by stoichiometry. You can see number of moles, the ratio is 1:1:1. Whatever is the number of moles of O2 reacting, same as the number of moles of carbon reacting, and same as the number of moles of CO2 produced. Right? Right. What do I get? I get 0 here. I get 0.5 moles. That means 0.5 moles of carbon remain unreacted. And how much I get? I get 0.5 moles of CO2. Please remember, 1 mole was 44 grams. So 0.5 moles would be 22 grams of CO2. I just land up with 22 grams of CO2. That's all. Fine. Third says, 2 moles of carbon are burnt in 16 grams of dioxygen. Now please understand, in the third part, I'm just changing second part only into third part, and it has a very, very important message. If I increase the amount of carbon from 1 mole to 2 mole, please remember, carbon was already extra. We were left with certain amount of carbon. Now, instead of 0.5 mole, I would be left with 1.5 moles of carbon, because it is the excess reagent, which is less. The lesser reagent is called limiting reagent, and in both 2 and 3, limiting reagent is dioxygen. Limiting reagent gets exhausted, it is reduced to 0, and if there is no more oxygen, obviously more carbon cannot burn. The amount of carbon burned is exactly the same. Extra carbon just remains unreacted. At the end, amount of CO2 produced is again 0.5 mole or 22 grams only in part 3 also. This is a very good learning from here, that if you increase the excess reagent, amount of product is not changed. If you increase limiting reagent, only then more reaction takes place and the amount of product can be increased. So what is the answer? This is the answer for 2 and 3. They have same answer, 2 and 3, that is 22 grams of CO2. Calculate the mass of sodium acetate required to make 500 ml of 0.375 molar aqueous solution. Okay, molar mass of sodium acetate is 82.0245, my God, grams per mole. Such accurate values are being offered and suggested. How do we start? See, let me start writing with what is given to me. Given is and asked. I am asked to give you mass of CH3COONA. Right? And I have 500 ml of 0.375 moles per liter aqueous solution. Now, moles per liter, moles of what? Moles of solute, sodium acetate per liter. Now, molarity is mole by volume. So, can I find out number of moles? Number of moles is molarity into volume, which is 0.375 moles per liter into 500 milliliters. What do I get? Well, I get some 0.375 into 500 millimoles. Because milli goes with mole, milli is just multiplied by 10 to the minus 3. We don't like it. If you don't like it, we remove that milli and convert it to moles. 0.375 into 0.5 moles, because milli stands for 10 to the minus 3. Milli stands for 10 to the minus 3. So we multiply this by 10 to the minus 3, you get so many moles. Okay, fine. Now what? Well, so many moles of sodium acetate are there. What is the mass? Therefore, mass of sodium acetate, this was asked. The mass is number of moles into molar mass. Moles is 0.375 into 0.5. And molar mass is 82.0245 grams per mole. Oh my God, that is fancy, fascinating. How much is this? On calculation, this comes out to be 15.38 grams. This is the mass. Yes, this is the mass of sodium acetate required. And this one says calculate the concentration of nitric acid in moles per liter. Let's write down. Asked. What is asked? Concentration of nitric acid in moles per liter, which is indicated by capital M, in a sample which has a density. Now I'm given, what is given? Density is 1.41 grams per ml and mass percent of nitric acid is 69% by mass. Now this is very simple but nonetheless instructive as well as interesting. Why? This question actually pertains to conversion within concentration units. I am given 1 unit, grams per ml, that is density, as well as percentage by mass, and I am supposed to find molarity. My dears, there are so many ways to do this actually, and people mug up various formulae regarding the same, which is actually very atrocious. Instead, I'll tell you a very beautiful method, a standard method by which you can solve not just this, but any concentration exchange problem. If you're given molarity, you have to find molality. If you're given molality, you have to find molarity, vice versa, whatever. All these concentration unit interchanges you would be able to do without actually having to mug up any formula, except of course for definitions, no doubt. And what's that? Stay with me. See, the way you can do this is, first of all, let us make a very simple chart. And what is the chart? We will make, in fact, a table. Let me clean the space for you, so that at least you can get much of it. Let's write, say, mass, molar mass, moles and volume. These 4 ideas. Okay. And what do you have? We have solute, which is HNO3. We have solvent, which is water. And if I add them, what do I get? I get solution. So I have made this table. And now with this, let me proceed as per what is given. I'm given 69% nitric acid. So I could say, let me consider 100 grams of 100 grams of solution. If I have considered 100 grams of solution, mass of nitric acid is 69 grams. And remaining 100 minus 69, that is 31 grams, would be the mass of water. Sensible. Molar mass, nitric acid is 63, water is 18. How do you know this? You can add and calculate. I have done it so many times that I have come to remember this, but you can add and get that. That's very simple. What is mole? Mole is mass upon molar mass. I need number of moles of nitric acid actually. So 69 by 63. Now whatever this number comes out to be, they seem to be divisible by 3, but that's not that big a deal. This is 23 by 21. So many moles of nitric acid. And what actually do I need? I'm asked molarity, moles per liter. Moles per liter means moles of solute. Now I have moles of solute. And then I need to divide this by volume of solution. Now how do I get volume of solution? Please note, this is not volume of solute or volume of solvent. This is volume of solution. Solution means a mixture. So I need the volume. Now, how do I get the volume? Do I remember any formula for volume? And then suddenly I remember density is equal to mass by volume. So, volume is how much? Volume is mass by density. Okay, this rho is density? Yes, this rho is density. So, individual mass of solute and solvent is a nonsense idea. What actually I would need to find is mass of solution. Can I do that? Of course, yes, I can. So, I would say, sorry, not mass. I'm intending to find out density, right? Oh, sorry, volume. So, volume is mass, and this is not mass of solute or solvent. Density is the density of solution. So, volume also, I will get volume of solution, and mass has to be mass of solution. Mass of solution is 100 grams. So, I will just write down 100 grams divided by, what is density? Density is 1.41. 1.41 grams per ml. So, volume is 100 upon 1.41 ml. Oh my God, should I convert that to liter? Yes. 100 upon 1.41 ml is equal to 100 upon 1.41 into 10 raised to minus 3 liters, which is actually 1 upon 14.1 liters. 2 decimals gone here, 1 goes down. So, this is what you could see. I have moles, I have volume. So, what is molarity by definition? Now, I am free to write. What is molarity? Now, we are proceeding towards the last step, and that would be the step of answer. Well, let's say that. Molarity is moles of solute. How many moles? 23 upon 21 moles. Oh my God. Divided by volume of solution in liters. And how much is that? That is 1 upon 14.1 liters. How much is that? That is 14.1 into 23 upon 21. Sorry. This is what you get. Moles per liter. Now, please remember, till now I have not harassed you with any calculations. Please note, NCERT has questions copied from American or US textbooks, usually directly without any thinking. They have missed out on one very basic fact, that in foreign universities, calculators are allowed in exam. And in Indian context, calculators are not allowed. So, the students are supposed to do calculations by hand. In their effort and in their bid for copy pasting, they have forgotten this very, very basic fact. So, they give you very, very ugly calculations. Actually, this can be a blessing in disguise if you take up this challenge. Please note, first of all, I am not condoning what NCERT has done. They have been lazy, they have been foolish in blind copy paste. They did not intend to give you a better practice, they just did not want to do anything themselves. But if you actually take this as an excuse to practice good calculations on your own, you could find this very, very helpful in general your practice. Say, for example, if I accurately want to calculate this, for number one, for those of you who are just interested in the answer, I'll first give you the answer. And those of you who are interested in how will you hand calculate this, I'll also teach you how to hand calculate. The answer is 15.44. If you just want the answer and you want to run away, then this is for you. Answer is 15.44. If you just want a ready-made answer, you have it at the end. But if you want to learn how do I calculate this by hand without using calculator, do I have a method? Yes, my dear, I do have, and I'll keep telling you this till you learn it very nicely, right? So, honestly, this is a part of maths, not chemistry, but then this portion of chemistry utilizes maths. So yes, for numerical chemistry, such calculations are very useful, and I'll tell you some tricks. See, it's like this. This is 14.1 outside, 1 plus 2 upon 21. Could you take it like that? Yeah, we could. Now this is 14.1 plus not 2 by 21. Multiply this is 28.2 upon 21, right? And could I not break up this 28.2 by 21? If you just look closely enough, could I just say that 28.2 is approximately 28, and this goes by table of 7. 7 4s are 28, 7 3s are 21. This is 1.33. Oh my God, yes. Yes. So what do I get? So I get this as 14.1 plus 1.33, that I get 15.43. 15.44 is the answer. You missed by 0.01. Come on, yaar. Without using calculator, we did a very accurate calculation. Second decimal place and all you can skip. That's not a big deal. Hai? Is this the answer? Yes. Still, if you're not satisfied, you say, no, I want more accurate. Then split it like this. Instead of neglecting it, just say that this is, so this much you have calculated, right? Now, all you need to do is to do this dirty work, right? How much is that? I can again approximate. See, this is a very beautiful method I'm telling you. How will I approximate now? This is such a dirty number. No, it is not dirty at all. See, I could say 0.2 is approximately 0.21, right? So 0.2 upon 21 is so much, which is 0.01. Can I say that? Yes. So I just add 0.01. That is 15.443 molar. I have now a more accurate answer than 2 decimals rounding off. Is that fine? Yeah. So even without calculator, can I do calculations? Yes, you very much can. First of all, have this in your heart, have the courage. Yes, we'll do this. And yes, you would be able to do that. With this idea, let's take up the next question. How much copper can be obtained from 100 grams of copper sulfate? Oh my God. Now that's very, very easy and very interesting at the same time. You're asked, what is given? Given is 100 grams of copper sulfate. What is asked? Asked is mass of copper. I could use principle of atomic conservation. I can say that whatever is the mass of copper here, maximum that mass of copper can be obtained. But how do I get mass of copper in copper sulfate? Well, I have to resort to moles. I'll say 100 grams of copper sulfate and molar mass of CuSO4 if I wish to discover it. Okay, how much would be molar mass of CuSO4? Copper is 63.5 and sulfate would be 96. If I add this is 159.5. Okay, that's a fairly ugly number, very close to 160, but yet not there. So, moles of copper sulfate is mass by molar mass, which is 100 grams, divided by 159.5 grams per mole. Is that fine? Of course, yes. Which is 100. Yeah, 1 upon 1.595 moles. Now, 1 mole of copper sulfate molecules contain 1 mole of copper atoms. So, this is equal to moles of copper atoms. Yes. So, mass of copper atoms would be, therefore, mass of copper atoms is moles into 63.5 grams per mole, which is 63.5 upon 1.595. Oh my God, that is one ugly stuff. But this is a calculation I need to do. And if answer is the only thing that interests you, well, let me give you the answer. It is simply nicely and happily 39.81 grams. The question ends here. But if you're curious, how did I calculate using hand? I can help you there. Again, it's not a part of chemistry, but these mathematical calculations are very simple. And my job here also is to give you a practice on how to do this. Let's do it together. If I have 63.5 divided by 1.595, how do actually I carry out this division? First of all, I realize 595 is like like pushing to, if I just round it off, this is 63.5 by 1.6. Oh my God, is that the case? Yes, that is very much the case. Now, I also realize that 16 fours are 64. So, this is 64 minus 0.5. Why we are writing it like this? I just felt that, 16 can divide 64 perfectly. The 16 fours are 64. This is 40 minus 0.5 upon 1.6. Now we are talking. Okay. Is this good enough? And then suddenly I realize that when I start reading table, 16 2s are 32, 16 3s are 48. Oh, 0.5 by 1.6 is approximately 0.48. No, it's accurately actually 0.48 plus 0.02 upon 16 3s are 48. So this is 0.3 plus 0.02 upon 1.6. Oh my God, this is negligible actually. If you just neglect this, it is simply 0.3. So this is 40 minus 0.3, which is 39.7. That's cutting it close. But then, could we not make it more accurate? Yes. One first approximation would be just roughly 40. If you're happy with 40, it's not a bad answer. But then you say, no, it's 39 point something. We have got this 39.7. No, I want this more accurate. I could have helped that also. Please calculate this. 0.02 by 1.6. How do I get that close? That is, this is 0.01 by 0.8, which is 0.1 by 8. Now 1 by 8 is 0.125. This is 0.0125. If you're so keen, you subtract that also from this. So 39.7 minus 0.0125. If you are so happy about this, let's round this out to 0.013. So this is 39.687. That should make you more than happy. It's very close to our accurate answer. That was 39.8 around. This is 39.7. We have cut it pretty close. That's the way you calculate by hand. One more thing. When you are calculating by hand, is the answer expected to match till 5th decimal space? No, not really. If you are within 1% of the exact answer, that's pretty accurate, and we are very much well within that range. Question number 8, so-called 8, says, determine the molecular formula of an oxide of iron in which the mass percent of iron and oxygen are 69.9 and 30.1 respectively. Exactly same numbers, same question, precisely the same question with one slight difference in grammar is question number 3. So this question is actually nothing but repetition of question number 3. I would say the NCERT has repeated questions. Yes, after 4-5 questions they have repeated this. As I said, NCERT is a beautiful cut paste from different sources without thinking. So I keep on saying that often, and people are often very furious that I make such stark blasphemous statements. But then why I get angry at this is because you are offering a textbook to millions of students and thousands of teachers. And if this is the kind of respect you have for such a large country, that you let your textbooks rot like this, it's bad, it's very bad. But nonetheless, have fun. This is equal to question number, this is equal to question number 1.3. So please go back to question number 1.3 and see the solution. One difference, in there we had empirical formula and here you have molecular formula. Now you might say, okay, no sir, there's difference. That was empirical formula, this is molecular formula. My dear, for ionic compounds, empirical formula is same as molecular formula. All you find is a ratio. There is no separate molecule for oxides, metal oxides like this. The answer is Fe2O3 and it stays as Fe2O3 only and nothing else. There is nothing new. Take a look. Calculate the average atomic mass of chlorine using the following data. And you're given percentage natural abundance and molar mass. Oh my God. What is percentage natural abundance? See, in nature, there is a certain ratio in which two nuclei of chlorine, Cl35 and Cl37 are found. And that ratio is 75.77 is to 24.23. How did somebody get this ratio? No. When Earth was formed, this was the composition with which it got formed. This is, you can say, Creator's will. This is how the Creator created our Earth. So this ratio has been given by God. We just experimentally measure it and use it. Humans can't alter it unless you keep on exploding nuclear bombs and you try to convert Earth into sun, which is a very devastating idea. But unless you do that, there is no way you can change this ratio. It is a natural constant. Molar masses are given to you. You're supposed to find average molar mass. How do we find average? There's a formula. M average is M1 x1 plus M2 x2, where x1 and x2 are mole fractions. Mole fractions of what? Of Cl35 and Cl37 respectively. Are these fractions given? If you add them up, they add up to 100. So this is percentage. Percentage divided by 100 will give you fraction. So fraction for this will be, simply I divide them by 100. That's it. So I use this formula, M1 34.9689 into 75.77 plus M2x2 36.9659 fanciful into 24.23. Wow, what I do? Just multiply them and then add. What shall we get? We will get the final average molar mass of chlorine. And that comes out to be 35.4527. That's the answer. Yes, that's the answer. The question says, if 3 moles of ethane, so in 3 moles of ethane, calculate the following. I have 3 moles of ethane. That's very lovely. Okay. 3 times C2H6. The number of moles of carbon atoms. How do we do that? If you have 3 moles of C2H6 and 1 molecule of C2H6 contains 2 atoms of carbon, so 3 into 2, 6 mole of carbon atoms. We directly multiply. This number which is outside, we can directly multiply. Yes. 3 into 2, 3 into 6, 3 into 6, 18 moles of hydrogen atoms. Yes, 18 moles of hydrogen atoms. And number of molecules of ethane, that's even more lovely. How do I find out number of molecules? Number of moles into Avogadro's number is number of molecules. I just have to multiply this by Avogadro's number. And how much is that? If I have 3 moles, 3 moles into 6.022 into 10 raised to 23 per mole. How much is that? If I multiply, I get 0.6618 into 10 raised to 24 molecules. Is that fine? That's fine. There we are. What is the concentration of sugar in moles per liter if its 20 grams are dissolved in enough water to make a final volume up to 2 liters? It's as simple as it gets. What I have been asked, moles per liter. So asked is concentration of sugar in moles per liter or molarity. And what has been given? I have been given, yes, what all have I been given? I have been given 20 grams. This is mass of sugar. I have also been given formula. C12H22O11 is the formula of sugar. And volume is 2 liter. How do I solve it? First of all, I need to find out the molar mass of sugar. C12, so 12 into 12 grams per mole. Atomic mass of carbon is 12. 22 into 1 grams per mole. 11 into 16 grams per mole. Let me add up all this. 12 12s are 144, 22 and 176. I add up everything, I get 342 grams per mole. Oh wow, you can add really fast. I remember this because I have solved this hundreds of times. But nonetheless, if you add, you get 342, right? Now, this is the molar mass of sugar, and I have been given 20 grams of sugar. Now, this is first step. Second step is moles of sugar is mass by molar mass, which is 20 grams by 342 grams per mole, and that comes out to be 1 by 17.1 moles. So many moles of sugar. That's it. Now, final volume is 2 liters. So concentration of sugar or molarity of sugar is number of moles divided by volume in liter. 1 by 17.1 moles divided by 2 liters, which is 1 upon 34.2 molar. This comes out to be the molarity of sugar. How much is this? The last part is not just calculation. How do I calculate this? Just see. This is 1 upon 0.342 into 10 raised to minus 2. Now I know one thing. 1 upon 0.333 into 10 raised to minus 2, this would have been equal to 3. Closely. So this roughly would have been 0.03. Now denominator is very slightly more than that. So the answer will be, the numerator will be very slightly less now. So it will be 2.9 something into 10 raised to minus 2. That would be the molarity, and this is what we guess. The accurate answer is 2.925. So that would be 0.02925 molar. Is that the answer? Yes, that is the answer. Approximate answer is, of course, 0.03, more accurately 0.02925 moles per liter. If the density of methanol is 0.093 kg per liter, very interesting. What is its volume needed for making 2.5 liter of its 0.25 molar solution? Very easy. Nonetheless, a different flavor. What I have been given? I have been given density of methanol is 0.793 kg per liter. Okay. Then please note, this is density of pure ethanol. Remember, this is pure, no water. And then I have 2.5 liter of 0.25 molar methanol. Now, when you say itne liters, itne moles per liter, this is suggestive that this is a solution, and if nothing has been mentioned, we simply take it as an aqueous solution. It is water dissolved in it. It has water dissolved in it. Now, molarity is equal to moles by volume in liters. So, therefore, number of moles is molarity into volume. Molarity is how much? 0.25 moles per liter, and this is 2.5 liters. 25s are 625. So that is 0.625 moles. So many moles of methanol have to be there. I'm given kg per liter or grams per liter. So if I have the moles, I need to convert them to mass. Okay. So mass of MEOH is moles of MEOH into molar mass of methanol. What is molar mass of methanol? carbon is 12, 4 hydrogens and 1 oxygen. That makes it how much? 32. Right? So molar mass is 32. Let me just multiply that. So I have 0.625 into 32. Now some of you might find this multiplication a little ugly. I always advise my students, avoid first multiplying then dividing, it is double. So just let us leave it like that. As a matter of fact, if you want, 0.625 also can be simply left as 0.25 into 2.5. In fact, you would find it much simpler. 0.25 into 2.5. What I have done, this number I obtained by multiplying these two. Let me just keep it as a multiple only, it is easier. 32, you know 8 fours are 32, right? So 32 is actually 4 into 2. What are you doing? I have just done factors. Why have you done that? 2.5 forza is 10. Is it? Yes. So I'll just say this is 0.25 into 4. 2.5 into 4. I've just clubbed these. 0.25 into 4 is 1. This is 10. 10 into 2, 20. That makes it very simple. This is 20 grams. Oh my God, I have 20 grams of methanol? Yes, I just have exactly 20 grams of methanol. Very clean calculation. Now, 20 grams of methanol. I have mass, I have density, and what they have asked me is volume. So volume is mass of methanol divided by density of methanol. Please note, volume is of pure methanol. This is not solution. So mass is of pure methanol and density is of pure methanol. This is 20 grams divided by, I have 0.793 kg per liter, kilograms per liter, which is 793 grams per liter. Oh, wow, how did you do that? That's not very difficult. Please remember, kilo is same as I am multiplying this by 1000. Kilo can be simply taken as multiplied by 10 raised to plus 3. Milli is 10 raised to minus 3. Kilo is 10 raised to plus 3. So I just did that, absorbed it here, so many grams per liter. I'll just use that. 793 grams per liter. Okay. So what is the volume I get? I get the volume as 20 upon 793 liters. This is the volume needed. Now again you will say this is ugly. Of course it is ugly. How do we solve it? Let me solve it for you. If you want the answer, of course there are people who just love the answer. I'll give you the answer also. Not just that, I'll also teach you the calculation tricks. Are you ready? There we are. See, we'll do it here. First of all, the calculation trick, because you'll not have such answers ready in exam. 20 by 793. Now 20 upon 793. 793, can you discover the closest round figure around 793? That is 800. Oh my God, so could we take that as 800? I mean, trying never harms you. This is 20 upon 800 minus 7. Can I say that? Yes. Which is actually 1 upon, this is 40 minus 7 divided by 20 is 0.35. 0.35. Okay. Which I can take as 1 upon 40, 1 upon 1 minus 0.35 upon 40. I can take 40 common, which is 1 by 40, 1 plus 0.35 upon 40. Oh, can we do that? Yes, we can do that. How exactly? I have used a theorem in maths which says that 1 upon 1 plus x is approximately 1 minus x if x is much less than 1. And if I have 1 upon 1 minus x, then that would become 1 plus x, provided x is very small. What is very small? Less than 1%. And do we have that case? We very much have that case. Okay, so how much is that? This is 1 upon 40. Now 0.35 is actually 3.5 by 10 or 7 by 20. So this is 0.35. 40 into 40, 1600. If you're willing to take that uglier number, sure. If you want, you can just neglect it. It's actually very negligible. So what do we write? We simply say 1 upon 40 is what? 0.025 liters. Right? The volume they wanted, 0.025 liters or 25 ml. No, I want more. If you want it more accurate, include this also. So many liters, if you multiply by 1000, it will be so many ml. So it will be I don't have space here, so I'll just do it. 0.35 upon 1.6 ml, which is 0.32 plus 0.03. 16 2s are 32, so this is 0.2. And this 3 also, if I just change it to 32, this is 0.2 plus 0.02. So I would get 25.22 ml roughly. Is that fine? Yeah. If you match this with a calculator answer, you will still get exactly the same answer. That is the beauty of hand calculations. Oh my God, this is so long. I had to write all this so that I can explain you. This is all in mind. It is mental mathematics, my dear. And I assure you, if you stick on with me and try these tricks and methods, you would be very good at these calculations by the time we finish our virtues in physical chemistry. Pressure is determined as force per unit area for the surface. The SI unit of pressure, Pascal, is as shown below. 1 Pascal is 1 Newton per meter square. Fine. If the mass of air at sea level is, this is most interesting, please note, 1034 grams per centimeter square. Now these units are really strange and odd. Calculate the pressure in Pascal. What is this meaning? Mass is measured in grams. What is this nonsense of grams per centimeter square? What does it mean? Actually, the question has nothing special to solve. The only good thing about this question is the interpretation of how do you interpret this strange unit, grams per centimeter square. Now, when you measure your own mass, you say, I weigh, say, 50 kilograms. It is 50 kilograms. You don't say, I weigh 50 kilograms per centimeter square or 50 kilograms per meter square, nothing like that. This is really not the unit, right, of mass. But what is the interpretation? The interpretation, my dear, is very simple and equally interesting. You are on Earth, right? And on this nice, happy Earth, there is something called as atmosphere, right? And this extends to pretty high, value, many kilometers, right? Now, if you take 1 centimeter square here, and you take a column from here till infinity, all the air, I have taken 1 centimeter square area, and if I take all the air up till vacuum, till I go to space, sky, out of Earth, all the air on that has a mass of 1034 grams. So if I take all this air, this complete air column, this has a mass of 1034 grams, and all this mass exerts a force here because it is being attracted by Earth, right? And let's not worry about variation of gravity. Effectively, this is the net mass I would feel at the bottom. They have asked you the weight, the pressure, which is nothing but force per unit area. Force is, mg. Mass is 1034 grams per centimeter square into acceleration due to gravity is 9.8 meters per second square. Now, I would need to convert this to SI units actually. 1034 grams is into 10 raised to minus 3 kilograms. And centimeter square is 10 raised to minus 4 meter square into 9.8 meters per second square. Right? If I do that, I'll get 1034 into 98 Newton. mg is force, and this is per meter square, Newton per meter square. So much. This is what I would get. Are you with me? Yeah. And how much would that be? Kg meter per second square is Newton per meter square. This is what I get. This is pressure in pascals. Yes, this is pressure in pascals. So therefore, the pressure in pascals comes out to be, because in mass, area is already included. So actually this is mass per unit area. So I get force per unit area, which is nothing but pressure. So pressure comes out to be this, very funny number. If I take 1.034 into 0.98 into 10 raised to 5 pascals. This is it. What do? I just multiply that. That is quite cool. Yeah, that is quite cool. Do it. And you get 1.01332 into 10 raised to 5 pascals. Is that the answer? Yes. Oh, how did you multiply? You can simply multiply also. That's also simple. Oh no, you want a trick? I'll tell you the trick also. Stay with me. See, it's like this. Now, this is 1 plus 0.034 and 0.98 is 1 minus 0.02. Take it like this. Okay. Now, 1 into this is simply 0.98. 0.034 can be approximated as 0.033333, which is 1 by 3 actually. So this is actually 0.1 upon 3, 1 minus 0.02, which is 0.98, fine, plus 0.01 by 3 is 0.034, let's take it as it is, minus, in fact, you don't even need this approximation, just keep it as 0.034, that is much easier, into this one, minus 68, how much? 1, 2, 3, 4, 5 decimals, 1, 2, 3, 4, 5. That's ugly. Yeah, it is indeed. How much is this? This is 4 3s are 12. No, sorry. 4, 8, 3, 11, 9 plus 1, 10. 1.014 minus 0.00068, which is 1.01332. And what is the answer? 1.01332. You get that? If you do it like this, it's a lot simpler. There we are. What is the SI unit of mass? How is it defined? It's a simple theoretical answer. SI unit for mass is kilograms. It is abbreviated as kg. How is it defined? Arbitrarily, a platinum iridium cylinder, which is kept in double dumbbell jar in a Bureau of International Standards, that is at Paris. In that office, arbitrarily a mass is kept, which is assumed to be 1 kg, and that is something which has set the standards for kilograms. Prefix matching. Wow. Match the following prefixes with their multiples. Lovely. Micro. Micro stands for 10 raised to minus 6. It is often denoted by a symbol mu. Yes. Deca. Inamina deca. Deca stands for? Well, deca goes for 10. So it is simply 10 times. Mega. Mega has a symbol capital M. and this is 10 is to plus 6. I'm using different colors so that you're not confused. Everything is distinct and separate. Giga, 10 is to 9. It is very simple. Giga, G. This is G. Yes. This is 9. Yes. So giga is 10 is to 9. That's very simple to remember. Fine. What about femto? Femto is really small. Actually, the remaining one, 10 is to minus 15. Please remember, 10 is to minus 3 is milli, 10 is to minus 6 micro, 10 is to minus 9 nano, 10 is to minus 12 pico, and 10 is to minus 15 femto. Simple enough. On the positive side, 10 times is deca, that's fine. 1,000 times is kilo. 10 is to 6 times mega. Usually people stay at that, but 10 is to 9 times is giga. Huge. That's it. What do you mean by significant figures? Actually, significant figures are the number of digits which are known with certainty. What does that mean? Say, for example, if you're measuring some length, and say you measure a certain length to be, say, 24.6 centimeters. Now, there are 3 significant digits, 2, 4, 6. Fine. Accurately, you can say that is definitely 24 centimeter. The third digit, 0.6, is actually a little unreliable. One might have made certain errors, certain approximations, some certain rounding offs, whatever. 6 may or may not be very certain or accurate, but nonetheless, this figure would be said to have 3 significant figures. A sample of drinking water was found to be severely contaminated with chloroform. Oh my God, CHCl3, supposed to be a carcinogen in nature. Yes. What is carcinogenic? Something which causes cancer is carcinogenic. It does not mean that by simply touching chloroform you would get cancer. No. If you're constantly exposed to it, if you're constantly drinking water which contains chloroform, yes, that has a threat that it may cause cancer. The level of contamination was 15 ppm by mass. ppm, what is that? Parts per million. What does that mean? It means that 10 is to 6 grams of water sample contained 15 grams of chloroform. This is the meaning of 15 ppm. Express this in percentage by mass. Oh my God, that is very simple. What is the formula of percentage by mass? Percentage by mass is mass of solute divided by mass of solution into 100. Mass of solute, chloroform, is 15 grams. Mass of solution, which is actually water sample, is 1 million grams into 100. Fancy, what is that? 0.01. This is 15 into 10 to minus 4%. 15. 1, 2, 3, 4. 0.0015% chloroform, and that's it. It seems to be very negligible, but apparently that also becomes very dangerous for human life. Determine the molality of chloroform in water sample. Molality, oh my God, what is molality? Moles of solute divided by mass of solvent in kg. So how many moles of the solute are there? Now, let us take this as the sample, right? So, 1 million grams of water sample has 15 grams of chloroform. What is molar mass of chloroform? Can we calculate? Yes. 12 plus 1 plus 35.5 into 3. How much is that? 71. This is 35. 3s are 105. 106.5. 106.5. and 13, 119.5. This is 119.5 grams per mole, roughly 20. So moles of chloroform is CHCl3 is how much? 15 divided by 119.5 moles, so many moles. Mass of solvent in kg. Now I have 1 million grams of water. You might say that has 15 grams of chloroform. Even if you subtract 15 from 1 million, it is practically 1 million only. 15 is quite negligible as compared to 1 million. So mass of water is 10 raised to 6 grams or 10 raised to 3 kilograms. Yes. Then I would have got molality. What is molality? Molality would be moles of solute. How many moles? This looks like an ugly number. Let's not call it ugly. It is actually 15 divided by 120 minus 0.5. Oh wow. You're back to your tricks again. I mean, where will I go? Which is 1 upon 120 upon 15 minus 0.5 upon 15. Which is 1 upon, now 15 6s is 120. 15 6s are 90, right? 90, 15 8s are 120. This is 8 minus 1 by 30. 0.5 by 15, up and down I multiply by 2, 1 by 30. If I take 8 out, this is 1 by 8, 1 minus 1 upon 240. Okay, which is 1 by 8 into 1 plus 1 upon 240. In case you are very keen to discover the moles like this, the accurate value. Fine. So molality will be, say, moles of solute so much divided by mass of solvent in kg. How much is that? 1 by 8 is 0.125. So 1.25 into 10 raised to minus 4 molal. How did you do this? I neglected 1 by 240 is so negligible, and that also when multiplied by 1 by 8 will become even worse. So we just neglect this. 1 by 8 is so much, and that is the molality of chloroform solution. Express the following as scientific notation. What is scientific notation? It means that, like 0.0048 would be, I shift decimal 1, 2, 3. 4.8 into 10 raised to minus 3. This is scientific notation. Something something into 10 raised to something. And this something something, this number has to be between 1 and 10. It has to be 1 or more than 1, and it has to be definitely less than 10. 9.9999, till that point it could be. What about this? 1, 2, 3, 4, 5. So this comes out to be 2.34 into 10 to the power 5. Oh wow. 1, 2, 3. So this is 8.008 into 10 to the power 3. Lovely. How much is that? 1, 2. So this is 5 into 10 raised to 2. This is already scientific notation, 6.0012. There is no sense in writing into 10 to the power 0. That's actually very stupid. It is already present in scientific notation. That's it. How many significant figures are present in each of the following? Now, if you have a number like 0.0025, please note the significant figures are just these. 1, 2, 3. This is 2.5. If you want, you can write down like this. It has 2 significant figures. I'm writing down the answer here. 2. 208. It has 3 significant figures. 1, 2, 3, 4. It has 4 significant figures. Please note, 0 befores or 0 afters have no significance in significant figures. So 1, 2, 3. It has only 3 significant figures. Strange. What about these zeros? They have a value. This is 1,26,000, right? So it is not that these zeros are meaningless, But when you talk about significant figures, please remember, significant figures talked about the precision with which we are recording or the reliability with which we are recording or offering a given value. So if I have a number 126000, so do you see that, well, the numbers, if there are zeros after the number, you just neglect them. If there are zeros before, you neglect them, you just take this number 3. However, there is a difference. If you are having decimals, 500.0, what does it mean? If you just write, this is not equal to just 500 when you talk about significant figures. Why? 500, the number 500 has only one significant figure, 5. That's it. This has not one but 1, 2, 3, 4 significant figures. Why? When you write 500.0, it indicates that you have measured till a number after decimal. That is the precision with which you have measured a given entity. So 500.0, just 500 means, it's close to 500, that's it. But when you put a decimal with a 0, it makes it very definite that that level of precision has been maintained or attained. So it has not 1 but 1, 2, 3, 4. But you said something else. What did I say? I had said that if you have zeros before a number or after a number, don't count them. If you have zeros in middle, count them. Yes. And if you have a decimal with zeros, clear, then all those zeros also will be counted as a part of significant figures. The last one, 1, 2, 3, 4, 5. Oh wow, it has 5 significant figures? Yes, indeed, it has 5 significant figures. Now this one is also very simple. It says rounding up to 3 significant figures. Fine. Now, if I just round it off, it will be collapsed like this. So this would be 34.2, because this number 1, if I collapse this, it is approximated to 34.22. But I'm not supposed to keep 4 figures, I'm just supposed to keep 3. I'll just remove these 2. That's it. They'll be rounded off. And since they're less than 5, they'll just vanish. 3 significant figures means these have to be removed. So this would be 10.4. Wow. What about this? This has to go. But if you remove this, my dear, there is a problem. What? If you cut this out, this will be approximated, 9 will become 10. So it would become 0.0460. Please note, 0.046 has only 2 significant figures, but 0.0460, it would have clear-cut 3 significant figures. So if you are putting zeros after decimal, even if there is nothing after those zeros will be counted in significant figures. Don't feel that they are not significant. This 8 has to be approximated, so this would become 2810. So this has only 3. There's no decimal here, so 0 at the end is not counted as a part of significant figure. Done? Done. The following data are obtained when dinitrogen and dioxygen react, oh my God, together to form different compounds. Well, we have N2 and O2 reacting with each other to get different compounds. Fine. 14 grams, it reacts with so many grams of dioxygen. Then 28 and 28 give you with so many mass of dioxygen. Which law of chemical combination is obeyed by the above experimental data? Give its statement. Fascinating. Now, I can see that the compounds seem to be different. Why? Because 14 grams are combined with 16 and 14 again are combining with 32. Same mass of dinitrogen seems to combine with more than 1 types of masses of oxygen. This hints very clearly at more than 1 compounds, which means law of Yes, law of multiple proportions. So data 1 and 2 indicate law of multiple proportions. Now 28 and 28 grams if I take. Now 28 grams are giving me 32 grams. If I cut this to half, so 14 grams will give me 16 grams. So this is just, if you look at 1 and 2, they give you multiple proportions. If I take 1 and 3, they are giving me law of constant proportions. Why? If 14 reacts with 16, the double 28 would react with the double 32. That is law of constant proportions. This 14 gives me 40 grams. Oh my God, that's even worse. So 1, 2 ka 4. 1, 2 and 4 if taken together exhibit law of multiple proportions, while 1 and 3 if taken together exhibit law of constant proportions. So which law of chemical combination is obeyed? There are two laws actually which are obeyed. Law of constant proportions seems to be minor here. Major law is law of multiple proportions. What about the statement? I'll tell you the statement also. If two elements react and they produce more than one compounds, if two elements react to give more than one compounds, sometimes they're giving compound 1, sometimes compound 2, sometimes compound 3, that way, then the ratio of masses of the other compound, which combines with a fixed mass of a given compound. So what does law of multiple proportions state? It says that if two elements combine to form more than one compounds, then if I take fixed mass of one element, and measure different masses of the other element, then these masses M1, M2, M3 are in simple integer ratio. They are in simple integer ratio. Then they are in simple integer ratio. Like if you see here, the example is with 14 grams, that is the fixed mass of nitrogen. If with 14 grams of nitrogen, different masses of oxygen are combining, M1, M2, M3, leave out the third data, which is useless here. So they're in simple integer ratio, which is being told this is 2, this to 4, this to 5. This is law of multiple proportions. Fill in the blanks in the following conversions. 1 kilometer, how many millimeter, how many picometer? Very interesting. Can you convert? Yes. Now, millimeter, how much is millimeter? Millimeter is actually 10 raised to minus 3 meters. Okay. And 1 kilometer is how much? 1 kilometer is, kilo stands for 10 raised to 3. The 1 into 10 raised to 3 meter. Okay. And if I have to get this unit somehow, what do? I say this is 10 raised to 6. Sorry. Okay, let this 10 raised to 3 remain as it is. I'll just say it is 10 raised to 3 into, now I need 10 raised to minus 3 meter. So can I say this? 10 raised to 3 into 10 raised to minus 3 meter. This is just 1, right? So this is just 1. So 1. I'm just writing this. 1 meter. Are you fine with this? And since this number is millimeter, now what will I do? I'll simply state that This is, and combine this, 10 raised to 6 millimeter. 3 plus 3 is 6. If numbers multiply, powers can add. Is that simple? Yes. Do I have to mug up a formula? No, I don't have to. It's common sense. Oh, what did you do? Well, you watch this here. Picometer. Now, see, the thing is, always start with where you're going. Picometer, how much is pico? Pico is 10 raised to minus 12. Now, picometer is 10 raised to minus 12 meter, right? I could say that 1 kilometer, please understand, kilo means multiplied by 10 raised to 3. So this is 1 multiplied by 10 raised to 3 meter, which is 10 raised to 3 multiplied by 1 meter. Meter also you should consider as something which is multiplied. You can bring it up and forth and back. Now, can I say that 1 is same as 10 raised to 12 into 10 raised to minus 12? Same powers plus and minus if I take, they will cancel. I'll get 10 raised to 0, which is 1. And why would I do that? I would do that simply because I know that this number is picometer. So I would be left with 10 raised to 15 picometer. Oh wow, this is how I convert? Yes, this is how I convert. Is that simple? That's very simple and very valuable also. Please note, you find it very useful at times. How about the opposite? If I have a small thing and I want to get big things, I could do that. 1 milligram, let me start with this. 1 milligrams is 1 into 10 raised to minus 3 grams, which is 10 raised to minus 3 into 1 gram. I just exchanged them, ting, tang, right? Now, 1 gram, I have to convert this to kilograms. Now, kilo is 10 to the power plus 3. So, I feel like having 10 raised to plus 3 here. So, I could also have 10 raised to minus 3 so that this on multiplication will give me nothing but 1, right? Okay. But I know that this is kilograms. This is 10 raised to minus 3 into 10 raised to minus 3 kilogram. Oh my God, this is 10 raised to minus 6 kilograms. Yes, this becomes 10 raised to minus 6 kilograms. Okay. What about nanograms? Nano stands for 10 raised to minus 9 grams. Oh, what would I do? That's not very difficult. I'll again sing the same song again with a different tune. How do I start? 1 milligram is equal to 1. Now, milli stands for multiplied by 10 raised to minus 3. Gram also, just take it as multiplied by grams. Imagine this also is unit also being multiplied. That's it. That's the trick of doing it. And you may or may not write multiplication sign later. That's okay. That is the maths rule. Instead of 1, now I have to write 10 raised to minus 9. How will I do that? Instead of 1, I will say this is 10 raised to minus 9 into 10 raised to plus 9 grams. Right? Now, this thing is nanogram by definition. So, I get 10 raised to minus 3 plus 9 nanograms, which is 10 raised to 6 nanograms. As simple as that. 1 ml, milli stands for multiplied by 10 raised to minus 3 liters. Fine. And 1 liter, by definition, my dear remember, is 1 decimeter cube. That is the definition of liter. 1 liter is 1 decimeter cube. So instead of liter, if I write decimeter cube, so this is simply because liter is same as decimeter cube, 10 to minus 3 liters or 10 to minus 3 decimeter cube. This is a very valuable but a very simple conversion. But this technique is very important. Make sure that you have learnt it. If the speed of light is 3 lakh kilometers per second, calculate the distance covered by light in 2 nanoseconds. That's pretty stupid. Very simple also. Let's see. Distance is speed into time. 3.0 into 10 raised to 8 meters per second into 2.00 nanoseconds. And how much is nano? Nano is 10 raised to minus 9. So this is 3.0 into 10 raised to 8. Nano is 10 raised to minus 9 meters. So much would that be. This has 2 significant figures. This has 3 significant figures. If I multiply them, then we should always get lesser significant figures. Like this is 6.0 into how much is this? 10 raised to minus 1 meter, which is 0.60 meters. The best I would be able to get are only 2 significant figures. If 2 different numbers are multiplied and they have different number of significant figures, then the product has only as many significant figures as the lesser of the 2, the numbers which are being multiplied. This had 2, this had 3, I'll just get 2. So this is 0.60 meters. That's it. Yes, the light would have traveled simply 0.60 meters in 2 nanoseconds. In the reaction A plus B2 giving you AB2, identify the limiting reagent, if any, in the following reaction mixtures. Now, this is a very interesting question, which I dare say is a double meaning and double standard question. Double meaning question, what does that mean? I must admit that NCERT has used very vague and not a very accurate language, which is not a very scientific way of presenting it. But then, first I will present what NCERT answer gives you. And then I'll point out what is the error in that and what is the confusion it actually ingrains in the mind of the student. If you are a dumb student, if you are a student who does not think, this is great for you, no problem. But even if you have an iota of scientific aptitude and if you think logically, then you would be even more confused after solving this question. And this confusion will add to your hatred towards chemistry, and that would be the contribution of NCERT once again. First, a wrong, confusing, a bad, but the most popular NCERT solution. I will just do a routine solution as I am expected to do if I am brainless. Let me do that first. In a reaction A plus B2 giving you, first 300 atoms of A and 200 molecules of B. Now, please note, molecule is not B, molecule is actually B2. But we can say it's okay because B2 also consists of only B atoms. So A is an atom. They have specified atoms of A. So A is an atom. So B alone also should be an atom. Molecule is not B, but molecule is B2. But they have, it seems, not made any distinction between atoms and molecules. And that is why I have a problem with that. But nonetheless, as per NCERT. Now, A first part has nothing very objectionable. AB2, that's okay. They are clearly saying 300 atoms of A and 200 molecules. 200 molecules, that means now I have 200 molecules of B and they seem to react. Now, initially, this was the data. Fine. What would be the change? If as many of them as possible react, well, let 200 of them go away. So I will get 200 here. So I would be left with 100 atoms of A, molecules of B, rather B2 would be totally reacted away, and I would obtain 200 molecules of AB2. So limiting reagent is 200 molecules of B. This is fine. And the way they have written it, there is nothing bad, unscientific. It's okay, acceptable. Second, 2 moles of A and 3 moles of B. I thought I'll give you a stupid solution, but I can't stop myself. So I will just discuss. Now, if you have A plus B2 giving you AB2, this is the standard reaction I have been given, right? And I have been given that initially I have 2 moles of A, and I have been made clear in the previous part that these are nothing but, A is nothing but atom. So fine, so I have atoms of A. And I am given 3 mole of B. Now if A represent atoms, B also should represent atoms. Like it is something like, if B is something like Cl2, then I have Cl atoms. Now if you write only, see in part 1 they had clearly mentioned molecules, so there was no confusion. But the moment you say 3 moles of B, that actually, literally the way it is written, it actually means 3 moles of B atoms. And that would mean 1.5 moles of B2 molecules. But if you look at NCERT answer, this is not what they have intended. What they mean is 3 moles of B2. So either they should have made a correction or they are spreading confusion. Just to match answer, I will just make a correction here. 3 moles of B2, 3 moles. And this is not there initially. What is the change? Now in this case, the lesser one is A, so A reacts away completely, taking away equal amount of B and producing equal amount of AB2. So what reduces to 0? Since A is totally gone, I say the limiting reagent would be A as per NCERT. But please remember, whatever question they have actually printed, if you scientifically interpret it, leaving away dogma and stupidity, the answer would be B, because 3 moles of B would imply 1.5 moles of B2, and in that case that again would become limiting reagent. Right? I'm writing down only the answer as per NCERT answers. But again, NCERT is not bigger than chemistry or science. That is why I'm pointing out this error. And dear NCERT people, if you're listening and if you really care, please make this correction. Fine, we'll make the correction maybe. But then why say such nasty things about us? See, what offends me is this textbook is treated as a Bible by lakhs of students and thousands of teachers. Such errors are just a product of carelessness and nothing else. I know that the esteemed professors who write this book actually know all this. I hope that. But they just didn't care, and that's why these errors have creeped in. Anyways, let me take up the third part. 100 atoms of A and 100 molecules of B. 100 atoms of A and 100 molecules of B. Now again, it should have been B2, but since they have mentioned the word molecules, so I would say 100 molecules are there which contain B, so we have sufficient number of B atoms so that I get 100 molecules of B2. If you have 100 each, that means they will react in the ratio 1:1. That means एक तराचा एक तिरानी दोनों मर गए खत्म कहानी. What does that mean? It means none of them is limiting or both of them are limiting. They are in stoichiometric ratio, so there is no need for the concept of limiting reagent. Either you could say both are limiting or you could say both are not. No, it does not apply in this case. What about the fourth part? You say 5 moles. Fourth and fifth part we are going to do probably. I'm just making space for that. 5 moles of A and 2.5 moles of B. Again the danger, 2.5 moles of B actually would mean 1.25 moles of B2, which they have not. So I'll just make a correction. What they are intending is this, 2.5 moles. This is initial. How much would change? Very easily you could see that lesser is B2, so only 2.5 moles will react. So I would be left with 2.5 moles of unreacted A. Since B2 gets exhausted, the limiting reagent is B2. Other things they have not asked. 2.5 and 5, it gets the opposite. 2.5 and 5. 2.5 goes off. So I get A is reduced to 0. 2.5 moles of B2 remains. So yes, A again happens to be limiting reagent. So this is B, A, none or both, whatever you might say. This is B and this is again A. These are the limiting reagent in case you make a correction in the question so that it matches with the NCERT answer. Nitrogen and hydrogen react with each other to produce ammonia. Wow. We have given the reaction, we have been given the reaction N2 plus 3H2 giving you 2 times NH3. Fanciful. Calculate the mass of ammonia produced, okay, if 2 into 10 raised to 3 grams of dinitrogen, 2 into 10 raised to 3 grams of dinitrogen reacts with 10 raised to 3 grams of dihydrogen. Okay. I've been given their masses. Could I write down the number of moles? Of course I can. And actually with the equation, we should rather write down the number of moles other than mass. Let me clean this dirty space and convert it to moles first. Nitrogen, we have 2 into 10 raised to 3 grams. This is 2 into 10 raised to 3 upon molar mass of nitrogen, which is 2 into 10 raised to 3 upon 28. So many moles. This is 10 raised to 3 by 14 moles. So many moles of nitrogen are there. What about hydrogen? I had 1 into 10 raised to 3 grams of H2, which is 10 raised to 3 upon 2, because molar mass of hydrogen is only 2. So many moles of H2. If I want to have same numerator and same denominator, instead of 2 we have 14. So this is 7 by 14 into 10 raised to 3 moles of hydrogen. Do we have ammonia? No, initially we don't have ammonia. This is what is given. So in the previous questions we were directly given number of moles or atoms or molecules. Now we are given grams, and the first step is we have to convert grams to moles, and now we are supposed to apply them to stoichiometry. To calculate the mass of ammonia produced, okay, so I have to calculate how is the change, which is the limiting reagent. 1:3 is the ratio. If I have 1 nitrogen, mole of nitrogen, I need 3 moles of hydrogen. If I have so much, I need 3 times. Do I have 3 times? I actually have 7 times. So do I have sufficient hydrogen? I have very sufficient amount of hydrogen, don't you worry. So which reagent can react away completely? Nitrogen can react away completely, my dear, and 1 would give you 2. So this much will give you 2 by 14 into 10 raised to 3 moles of ammonia. Oh my God. And if so many are the moles, what is the mass? So mass of ammonia thus produces 2 by 14 into 10 raised to 3 into molar mass of ammonia is 17 grams per mole. I multiplied number of moles by molar mass, which is 17. I get so many grams of ammonia. How much would be that? 7 2s are 14, 17, 7 4s are 28, 20, 30, 7, 2.43. Close to this. Roughly 2.43 kilograms of ammonia would be produced. That is answer to question number 1. Will any of two reactants remain unreacted? Yes, hydrogen would remain unreacted. If yes, which one? Hydrogen. And what would be its mass? Mass of unreacted hydrogen has been asked. Well, that's not too difficult. We had 7 by 14. What reacted was 3 by 14. So we are left with 7 minus 3, 4 by 14 into 10 raised to 3 moles. So mass of H2 excess जो बच गई है वो कितनी है? That would be 4 by 14 into 10 raised to 3 grams, so moles into 2 grams per mole. That is molar mass of hydrogen. And that would be, yes my dear, 4 by 7 kilograms. How much would that be? Or 4 by 7 would be 7 5s are 35, 50. So 7 7s are 49, 7 1s are 7. So many kilograms. 0.5714 kg or 571.4 grams. So many grams of hydrogen would be left unreacted. How are 0.5 moles of sodium carbonate and 0.5 molar sodium carbonate different? That's very simple. Moles is an absolute number. If you say I have 0.5 moles of sodium carbonate, you have certain quantity of sodium carbonate. How much would that be? If you want, you can even calculate that. Na2CO3. Molar mass would be 23 into 2 plus 12 plus 16 into 3. That is 46, 12, 48, 60, 106. So molar mass of sodium carbonate is 106 grams per moles, which means 0.5 moles corresponds to 0.5 into 106 grams per mole, this is, which is 53 grams. So if I have 53 grams of sodium carbonate, that's it. I would say I have 0.5 moles of sodium carbonate. Fancy. And if I have 0.5 molar sodium carbonate, 0.5 molar means 0.5 moles per liter of sodium carbonate. That means if I take 1 liter of the given solution, in the first case, sodium carbonate is a simple solid. In the second case, you're talking about a solution. So I have to have a solution, and if I take 1 liter, that would contain 0.5 mole of sodium carbonate or 53 grams. You can take different amounts of that solution and you would be able to obtain different amounts of sodium carbonate, because the actual quantity of sodium carbonate is not mentioned here. It is just concentration which is mentioned, and the amount or the number of moles or the mass of sodium carbonate which you have would depend upon how much is the volume of the solution which you possess in this second case. That is the difference. If 10 volumes of dihydrogen gas react with 5 volumes of dioxygen gas, how many volumes of water vapor would be produced? Now in this case we are assuming that all of them are gaseous. H2 gas plus half O2 gas gives you H2O gas, or steam as they call it, right? Water vapor. 10 volumes. What is the meaning of volume? It means it could be any volume, means it could be ml, it could be liters. Like, it is just indicating a kind of ratio. If 10 ml of dihydrogen is there, then I would have 5 ml. If 10 liters, then I have 5 liters, that way. So 10 volume reacts with 5 volume. Okay. This is initial. How much would we change? If 10 goes away, half of 10 goes away and 10 is produced. 0, 0, oh my God. So I would get 10 volumes of water vapor. Please note, stoichiometry is directly applicable on volumes of gases also. Why? Because stoichiometry can be directly applied to number of moles And for gases, number of moles is directly proportional to volume at same temperature and pressure. And assuming all of them are same temperature and pressure, we can simply talk in terms of volumes of gases also instead of moles, because they are directly proportional to number of moles anyway, which means that our stoichiometry rules will also apply to volumes of gases. The answer is, in this case, 10 volumes of water vapor would be produced. That's it. Convert the following into basic units. We have 28.7 picometer. Now 28.7 picometer is 28.7 into pico is 10 to the minus 12. Oh yes. And that would mean 2.87 into 10 to the minus 11 meters. Oh, after 1 decimal, the number between 1 and 10 should be used here into 10 to something something, and that is the answer of 1. 15.15 picometer again. And let me take third also along with 25365 milligrams. Well, they're very easy, so I'm doing it together. This 15.15 into 10 to the minus 12 meter again, and this is 25365 into 10 to the minus 3 grams. And we would need standard units, means this has to be converted to actually kilograms. We'll see that. How much is this? This is 1.515 into 10 to the minus 11 meters. Again, not a big deal. Fine. The third one, 1, 2, 3, this is 25.365 grams. This is, in case grams is fine. In case somebody is very much gaga about kilograms, 0.025365 kilograms. This is how you would convert them. How? Shift decimal by 3 units, 1, 2 and 3. So you get a 0 also here, and then put the decimal, and grams can go to kilograms. That's it. Which one of the following will have largest number of atoms? You have 1 gram of solid gold, 1 gram of sodium, 1 gram of lithium, and 1 gram of chlorine. If you want number of atoms, please note number of atoms is Avogadro's number into number of moles of atoms. And my dears, do make sure that you don't confuse this with the number of molecules. Moles of atoms, very clearly. And what is the meaning of moles of atoms? It means mass of atoms upon atomic mass. It is not molecular mass. Please note, you're finding number of atoms, you will just use atomic mass. How much is that? Now, please note, gold, sodium, lithium and chlorine, all of them are elements. Yes. So, all I need to do is mass of each of them has same mass, 1 gram. So, and each of them has to be multiplied by, now mass of atoms is 1 gram each, Avogadro's number is same. So, do you see that number of atoms is now inversely proportional to atomic mass? Number of atoms is inversely proportional to atomic mass. So, if atomic mass is more, the number of atoms would be less. For gold, atomic mass is 197. Sodium is 23, lithium is 7, and chlorine is 35.5. Don't take 71. We don't need molecular mass, we just need atomic mass. The largest number of atoms would be possessed by something which has minimum atomic mass, and minimum atomic mass is possessed by lithium. So lithium is the winner. Lithium will have largest number of atoms. You can do that even without actually making the calculation, because the data is 1 grams of each. It's very simple. Calculate the molarity of a solution of ethanol in water, in which the mole fraction of ethanol is 0.04. Assume that density of water is 1. Very interesting. What is 1? 1 gram per ml, that is. Fine. So, how do we start? We say, let us consider 1 mole of solution. If I have 1 mole of solution, now mole fraction of anything, say of mole fraction of ethanol, is moles of ethanol divided by total moles of solution by a formula. This is the formula of mole fraction. Now total moles of solution, I am considering only 1 mole. So if this becomes 1 mole, so therefore moles of ethanol are equal to mole fraction. Mole fraction is 0.04 into 1. So I have moles of ethanol as 0.04 moles only. Okay, fine. And do I also have moles of water? Yes, moles of water is 1 minus 0.04, which is 0.96 moles. Fine. Now, they are saying assume density of water is 1. Moles of water is 0.96. Therefore, mass of water, how much is mass of water? Mass of water will be 0.96 moles into 18 grams per mole. Whatever it comes out to be, 18 into 0.96 grams. We will not multiply now. We will multiply only at the end. This is the mass of water. Now, density of water is 1 gram per ml. Therefore, volume of water will be mass by density will be 18 into 0.96 ml. This is the volume of, if you take only water, this seems to be the volume. Now, interestingly, they are talking about molarity of solution which involves volume of solutions. So we have to make one shameless assumption. And what is that? That volume of water is same as volume of solution. It's a dilute solution. This is not a very, very good assumption if you're mixing liquids. But then since we are left with no other option, we'll do this. So we have volume of solution, yes. We have moles of solute, yes. So therefore, molarity, please note I am making a drastic assumption without which this question cannot be solved, that this is equal to volume of solution also. Very shameless assumption, but no option. So this is 0.04 moles divided by 18 into 0.96 ml, which means so many liters, right? Well, we could simplify this further. How would that be? This is 40 by 0.96 into 18. 4 tens are 40 and 4 24s are. Is so much ugly calculations, but we can solve that and get the answer. And this comes out to be 2.314 molar. That is the end? Yes, that's the way it is. If that is sufficient for you, actually the question ends here. But as we always do, if you want me to do the calculations and show you the tricks of calculation, let me do that for you. I'm supposed to calculate this dirty number, 10 by 0.24 into 18. 10 by 0.24 into 18. As ugly as it gets. I think it is just a reciprocal like case. Now these numbers, I guess it is best to multiply, just multiply 24 and 18. 18 4s are 72, 18 to 36, 43. 36 plus 7, 43. Yeah, so this is 1 upon 0.432. That is a formidable number. Yes, it is indeed. Had it been 1 by 0.4, the answer would have been 2.5. So first of all, immediately roughly do a calculation. I should get somewhere around 2.5, somewhere, more or less. Now, how would I make further calculation? Well, let's check, look and learn. This is the nearest dividable thing which I discover would be around 0.5, is it? So, or this is 0.4 plus 0.032. If I take 0.4 outside, it is 1 plus 0.032 upon 0.4, which is 1 upon 0.4, 1 minus. Now, if I divide this, 4 8s are 32, right? So that means 0.08. Please remember, 1 by 1 minus x is approximately 1 plus x. I have used this here. So this plus has changed to minus. I divided them, so I got this number. Fine. How much is this? Is 1 upon 0.4 minus 0.08 upon 0.4. Okay, how much is this? This is 0.25 minus, how much is this? This is 0.4 2s are 8, right? How much is that? Is that 0.2 minus 0.02? Yeah, so that gives me 0.23 molar. Oh wow, I got 0.23? Yes. Which was but there is 1.4 also. So don't approximate here. Do more binomial expansions, you'll get more accurate, but 2.3 is sufficiently accurate answer for you. That's how you get that. What will be the mass of one C12 atom in grams? Now, most interesting. We know very well that Avogadro's number, Na atoms of C12 have exact mass of 12 grams. This is 6.022 into 10 raised to 23 atoms. They have 12 grams. So one atom would weigh how much? 12 into 1 upon 6.022 into 10 raised to 23 grams. As simple as that. How would that be? Well, not very exciting. If you just look, let us divide numerator and denominator both by 6. So 12 by 6 is 2, and this is 1.0. Now 2, 6 3s are 18, 19, 20, 21, 22, 0, 3 of course, 3 and 40, then 7, 6, roughly this much, okay, which is 2 upon 1 plus 0.0037, which is 2 into 1 minus 0.0037. How did you do that? Oh, come on, there's a maths theorem. 1 by 1 plus x is approximately 1 minus x. If x is much less than 1, I'm telling you the calculation trick. 2 minus 0.00, 37 2s are 74. So I get 74 like this. Into 10 raised to minus 23 grams. How much is that? 1.9926 into 10 raised to minus 23 grams. Is that fine? That's absolutely fine. This is what we get. How many significant figures should be present in the answer to the following calculations? Now please remember, dears, when you talk about significant figures and mathematical operations, rules are simple but very clear. If you are multiplying or dividing, fine. You multiply and divide happily without considering anything. You might get a long number, whatever. But first check, how many significant figures are present with the first number? The rules say that if you have numbers after decimal, fine, then all the zeros on the left side should be omitted. All the zeros should be right side, on the right side should be counted. So 1, 2, 3, 4. This digit has 4 significant figures. This digit 1, 2, 3, 4, 5, it has 5 significant figures. this has 3 significant figures and this has 4 significant figures. All right. Now, if you are multiplying or dividing them, you will get some answer. You might get any answer as, and by using calculator, you could actually find the answer till 10 decimal digits also. But the answer must not contain more significant figures than the minimum number amongst these. So 4, 5, 3, 4. The minimum number is 3. So the maximum number of significant figures that this can have is 3. Please, I'm not saying this multiplication or division comes out with 3. The number of significant figures in the answer, the maximum possibility is 3. That's it. This is the first question. Second question comes with a lot of debate. Why? NCERT offers one answer and actually this is ambiguous. Why? I'll tell you. There are 2 numbers, 5 and 5.364. Now, this number 5, how many significant figures does it possess? 5.364 is very clear, it has 4 significant figures. This number 5, does it contain 1 significant figure? Actually, the fun part is, NCERT has assumed that it has infinite significant figures. Why? See, I'll tell you, the rule is very simple, but they have made to look very dirty here. The actual rule for significant figures is, if you are obtaining a number by counting, say for example, I'm saying how many students are present in this class, and if that number is 5, it is precisely 5. You can't have 5.1 or 5.001 students because students will be whole numbers, right? So, this number 5, the accuracy or the precision of this number is infinite. How many bananas are present in a dozen? When I say 12, that is infinite precision, right? Why? Because I mean, it's always 12. I can't have 12 point some number. It's a number. It's by counting. On the other hand, if I say the length of this cloth is, if somebody says 5 meters, the length of this cloth in meters is, and somebody says 5, then that 5, although it looks like an integer, it may or may not be a precise number because cloth could be 5.0 something meters also. So if an integer is obtained and it is known that it is integer only and it is not a product of measurement of any measurable quantity, it could be precise, it could be imprecise. So if 5 represents an integer which is a product of counting, it depends upon the scientific process by which you have encountered this number. In that case, the precision of 5 would be infinite. Infinity and 4, the smaller number is 4. So the number of significant figures in this would be 4. Yes. But however, there would be a source from this, from which our NCERT people would have copied this. And they have not wondered and they have not bothered to clarify this 5 comes from where. If this 5 is a result of some measurement of a physical quantity, say for example, the volume of this sample of water is, in liters is, and say if that comes out to be 5, in that case, this might not be an exact whole number. It could be 5 point anything also. In that case, the number of significant figures of this would be 1. And in that case, the answer would change from 4 to 1. But again, this is NCERT. NCERT is a lovely book which eats away half the data, gives you answers, assume half, and expects you to discover it for your own, which leaves the students confused. But again, there's nothing new about NCERT. So I've told you the rule clearly and a potential error of omission. This is a double meaning question which they have given and they have not specified. If you interpret as per the meaning of writer's brain, which is a very stupid way of writing anything in science. I mean, I would not have to figure out the brain of the writer. Science means exact. It is an open-ended question which can have 2 answers. But going by NCERT's brain, the answer would be 4, and they've assumed 5 to be an exact number, which I've just explained may or may not be exact. And the third question is a real magic. As per NCERT, the answer is 4. My condolences. Use the data given in the following table to calculate the molar mass of naturally occurring argon isotopes. Tang, tang, tang. So I have argon 36, 38, 40. Their accurate isotopic molar masses are given and the percentage abundance has been mentioned. I'm supposed to find the average atomic mass. How do I do that? We have a formula as we have seen before. What's that? See. A average is A1 x1 plus A2 x2 plus A3 x3. How do you get x1, x2, x3? I get that from percentage abundance. Percentage divided by 100 will give me fraction. So x1 is 0.337 upon 100. x2 is 0.063 upon 100 and x3 is 99.6 upon 100. Oh wow, I just substitute. A1, God bless me, 35.96755 into 0.337 by 100, kill me. It's as ugly as it gets. A2 is 37.96272 into 0.063 by 100. Wow. And this is 39.96. 9624 into 0.996. Loveliest of all. Actually, if you care to see, these numbers, now you can add them. This is simple calculation. Simple. Not so simple actually. But I mean, it's actually a fairly dirty number if you look at it. Yes, indeed. Can I get a close answer? I can tell you a method, of course. And what is that? Just watch. You're free to use calculator or hand calculations and solve this very accurately. You're most welcome. Please do it. If you do that, you will get the answer as 39.947 grams per mole. This is the answer. Oh wow, let's mug this up. It's a stupid thing to mug up such answers, obviously. You need to be able to calculate them. A question is done as per NCERT. It's very well done. The dirtiest part remains, yes, the old villain calculations. How do we do that? Let me help you out with them. See, first of all, such, ugly figures. See, if you have something which is less than even 1%, please note 0.337, 0.063%, they are not going to significantly contribute to overall mass, please remember. So ultimately, since most of it is argon 40, the answer would be very close to 40 anyway. So it is 39.96, the answer should come very close to 39.96 anyways. Now the final answer will be equal to this, more than this or less than this. See, you are trying to mix it with something which is lighter, right? So the final answer, the final average, now this is the heaviest. If the heaviest thing is mixed with lighter components, even if lighter components are very small in number, the final answer should be at least slightly, very slightly less than this number. 39.9624 from the 39.9, see, 624 has been changed to 47, that's it. 39.9 continues, as I said. So by common sense, the answer should be close. It is actually seemingly close. How do I calculate that? Now that remains a challenge. Let's see if we are up to the challenge. Now comes कि अब इसको simplify कैसे करोगे? देखो, ऐसे देखो कि पहली बात तो ये हैं तो बहुत छोटी संख्याएं, जी हाँ, बहुत घिनौनी भी लग रही हैं, बिल्कुल. थोड़ा सिंप्लीफाई करना शुरू करते हैं तो एक तो ये है 39.962, 37.962, 35.96. इनको एक काम करें, जो ये इधर की दो में ना, इनको तो साफ कर देते हैं. अपन इन नंबरों को देखने नहीं चाहते एक लिमिट के बाद, ठीक. 5 सिग्निफिकेंट फिगर्स बहुत हैं, उसके बाद जो 6-6, 7-7 फिगर दी हुई हैं उसको नेग्लेक्ट कर देते हैं। अच्छा, एक चीज़ और दिखती है क्या, तुम इसको देखो, जैसे ये 37 पॉइंट समथिंग, 35.96 है ना, जस्ट इसके लिए 35.96 मानता हूँ ये 7-1 है, जस्ट होमोजेनस रख लेंगे, 2 कर लो इसे एक बार को, this into 0.337 by 100 प्लस 37 है ना ये, तो इसको भी मैं कर लूँ 35.962 प्लस 2, कुछ भी ऐसा कर लूँ, इंटू 0.063 बाय 100, चलेगा? ऐसा क्यों कर रहे हो? मैं इसलिए कर रहा हूँ 35.962 यहाँ पे कॉमन ले लो, 0.337 और 0.063 जोड़ोगे तो ये आ जाएगा 0.4 प्लस 2 इंटू 0.063 अपॉन 100 बचेगा। ये बहुत छोटी संख्या है, गोली मारो, निगलेक्ट कर दो इसे। तो जो भी एक गंदगी है इसमें 0.004 आ जाएगा। तो ये लगभग कितना हो गया? ये लगभग हो गया 80। अगर बहुत एक्यूरेट कैलकुलेशन करनी हो, मैं उसके लिए थोड़ा सा एक रफ तरीका बता रहा हूँ आपको, अदरवाइज तो मल्टीप्लाई करो, मस्त हो जाओ। तो इनको जोड़ जाड़ के इस गंदगी को सिंप्लीफाई करके मैंने कहा लगभग, क्योंकि वैसे भी इसका कंट्रीब्यूशन बहुत कम आने वाला है, इतना आ रहा है, कितना? 35.962 इंटू 0.004, लगभग थोड़ा सा एक्स्ट्रा भी आ रहा है, किसी के श्रद्धा हो तो वो भी जोड़ ले, ठीक है। यहाँ 35.962 है, यहाँ 39.962 है, तो क्या मैं इसको कह सकता हूं कि ये भी 39 ही है, -4 और है, 39 - 4 35 था, ऐसा। तो ये और ये जोड़ रहा हूं। अब इसका फायदा क्या होगा? दिस प्लस 39.962 इंटू 0.996, ये नंबर कॉमन निकल आएगा बाहर। इसको सिंप्लीफाई करो यहां पे, तो 39.962, वेरी लवली, इनटू कितना जाएगा? 0.004 प्लस 0.996, ये संख्या प्लस ये संख्या तो खप जाएगी, और माइनस बचेगा 4 इंटू 0.004, ये कितना आ गया? ये आ गया, ये जोड़ के 1 आ जाएगा, 39.962 माइनस 0.016, रक्षा कर प्रभु, ठीक है। जो भी आ रहा है, हो सकता है आपको इसको निगलेक्ट कर दिया तो लगा लेना, इसकी दो हल्का सा बढ़ा लेना बाद में, कोई नहीं। कितना आ गया? ये आ गया 39.942, नहीं 6, 39.946 ग्राम्स पर मोल। ये काफी कचरा झाड़ के आया है, थोड़ा जल्दी आ गया है, और मैं तो कैलकुलेटर से कर लेंगे, कैलकुलेटर से तो इलाज ही नहीं, तो कर लो, कोई दिक्कत नहीं है। हैंड कैलकुलेशन करने तो भी देखो, वी हैव कम वेरी क्लोज, रीजनेबली एक्यूरेट। 0.001 जो हल्का सा 5th सिग्निफिकेंट फिगर में फर्क लग रहा है, उसको ये हमने छोटा सा छोड़ा था, उसके कारण है। एक 1 बढ़ा लोगे तो वो भी आ जाएगा, बढ़िया काम है। एंड calculate the number of atoms in each of the following. You have 52 moles of argon, oh my god, 52 U, that is AMU of helium, and 52 grams of helium. Let's try that out. First of all, 52 moles of argon, 52 moles, number of atoms, N is Avogadro's number into number of moles, 6.022 into 10 raised to 23 into 52. So what do I need to do? Just multiply by 52. That's not very difficult. 12.044, and if I multiply by 550, that would be how much? 5 2s are 10, 4 2s are 10, 11, and 5 6 are 30. 4 4 2 3 1 3. Oh my God! How much is that? 300. So this is 313.244 into 10 raised to 23 atoms, or 3.13244 into 10 raised to 25 atoms. If I write down in standard scientific notation, this would be the number of atoms. Is that fine? That's perfectly fine. 52 AMU of helium. Now helium, atomic mass of helium is 4. So 4 AMU. So number of helium atoms is 52U by 4U, which is 13. Oh, helium has only 13 atoms. Yes, that's how it is. And third, 52 grams of helium. Helium is 4 AMU. Yes, it is also 4 grams per mole. If I take atoms, then mass is in AMU. If I take moles, then mass is in grams. So moles of helium is mass by molar mass, which is 52 grams by 4 grams per mole, which is 13 moles. So I have 13 moles of helium, which is 13 into 6.022 into 10 raised to 23 atoms. 13 to 26, 28, 13, 6 are 78. So I get how much? 78.288. This is what I get into 10 to 23 atoms, or if you want a scientific notation, then 7.8286 into 10 raised to 24 atoms. This is answer 3. There we are. Simple calculations. And there we have a welding fuel gas. Oh my God, what is that? Let's see. A welding fuel gas contains carbon and hydrogen only. So this is a hydrocarbon, and it might have a formula like CXHY. Burning a small sample of it in oxygen gives so much of carbon dioxide. If I burn this in oxygen, it gives me CO2, 3.38 grams. And I get water. And how much of water I get? 0.69 grams of water. Perfectly ugly. And no other products. So I'm very satisfied. I've burned it completely, and I get so much of CO2 and so much of water by burning it in oxygen. This is one data. A volume of 10 liters measured at STP of this welding gas is found to weigh 11.6 grams. So 10 liters corresponds to 11.6 grams. Calculate the empirical formula, molar mass and molecular formula. Can we do that? Of course we can do that. And how exactly would we do that? Using principle of atomic conservation. All the CO2 and H2O, all of CO2 contains carbon exclusively from hydrocarbon. So mass of CO2, how much is that? That is 3.38 grams. This is 3.38 by 44. What is 44? That is molar mass of CO2. So this is 3.38 divided by 44 moles of CO2. So many moles of CO2 molecules are there. And one CO2 molecule, please note, contains carbon from hydrocarbon and oxygen from O2, which was used for burning. We are not interested in O2. We are just interested in carbon. Therefore, I get moles of carbon. So I get moles of carbon as same 3.38 divided by 44. Perfect. Do I also get hydrogen? I might. Let's check. Mass of water. How much is that? That is 0.69 grams. Corresponds to 0.69 grams by, now molar mass of water is 18 grams per mole. So I get 0.69 by 18 moles of H2O. And one H2O contains 2 atoms of hydrogen. One H2O contains 2 atoms of hydrogen. So therefore, moles of H atoms in water is 0.69 upon 18 into 2. Because these are moles of water, multiplied by 2 will be moles of hydrogen atoms. And all these hydrogen atoms have come from hydrocarbon and nowhere else. So this must be the number of moles of hydrogen atoms in hydrocarbon. And how much is that? I'll just put that number 0.69 by 9. 2, 9s are 18. That's why I'm using this. If I need empirical formula, my dear, all I need to find is their ratio. Can I find the ratio? Of course I can. How? We divide. Actually, this number seems to be further divisible. That way they are both, but we'll simplify them at the end. Now, if I just want to find out the ratio, I'll divide both of them by moles of carbon. So, this number I'm dividing by the same number, so I get 1. And this number 0.69 by 9, I'm dividing by this number, same number. So I get, dividing by the number means multiplying by the reciprocal. So there's no space here, so I'll just write down, multiplied by 44. This thing into reciprocal, which is 44 by 3.38. This has got it congested here, I'll take this number here. How much is that? 0.69 by 9 into 44 by 3.38. Let us see how much it boils down to. Let us do away with both the decimals. This is 69 and this is 338. This is 23 by 3 into 44 by this really ugly number 338. Could we make it 22? Yes, let's see. 22 by 2. 169. Now 23, 169. Let's see how it solves up. तो आप इसको देखें 23 into 22. कुछ ऐसे कर सकता हूँ. 22 का स्क्वायर 484 प्लस 22 कितना हो जाएगा 506. अच्छा और 160 प्लस 9. नौ 60 से 480 तो 480 और 27 कितना होता है 507 और इतनी. This is 507. That is one only, yeah, come on. So, the ratio is 1:1. C and H mole ratio is 1:1. That would mean that the empirical formula is CH. How cheap. How can we get the molar mass? That is the second problem which we shall address now. Let me clean up some space so that we have some space. We've been busy doing rough, dirty calculations. And we were given 10 liters weighed 11.6 grams. Now 22.4 liters contain 1 mole. So they would weigh how much? 22.4 into 11.6 upon 10 grams. 1 mole would weigh so much, so this is nothing but molar mass. So molecular weight of the gas is 22.4 into 11.6, which is into 1.16, so many grams per mole. Wow, this is the molar mass? Yes. And what is the empirical formula mass? I mean, of course, we need to multiply the dirty thing and get that, but then this is what we roughly have. We calculate that 25.984, around 26 grams per mole. So molar mass is 26. Empirical formula is CH. So molecular formula will be CHN. So molecular mass will be C is 12, hydrogen is 1, 12 plus 1. Sorry, I'll write it again. 12 plus 1 into N, which is 13N. So molecular mass seems to be 13N. But molecular mass has been independently calculated to be 26. Therefore, N is equal to 2. Fanciful. C2H2. Acetylene is my gas, and actually we are aware also that acetylene indeed is used in welding. So we have oxyacetylene flame and things like that. So molecular formula is C2H2, empirical formula is CH, and molar mass is 26. These are the answers. Calcium carbonate reacts with aqueous HCl to give CaCl2 and CO2 as per the reaction, and we have a reaction. What mass of calcium carbonate is required to react completely with 25 ml of 0.75 molar HCl? So we are given volume of HCl as 25 ml. We are given concentration of HCl as 0.75 moles per liter. Therefore, moles of HCl, which is volume into concentration, which is 25 ml into 0.75 moles per liter, which is 25 into 0.75, ugly enough, 25 into 0.75 millimoles. Millimoles, don't forget milli. Milli means multiplied by 10 to the minus 3. So many millimoles of HCl is present. And they are talking about mass of calcium carbonate required. Now from the balanced equation, can you see 2 moles of HCl need 1 mole of calcium carbonate? What? Yes, 2 moles of HCl need 1 mole of calcium carbonate. That means 2 millimoles of HCl would need 1 millimole of calcium carbonate. So millimoles of CaCO3 is half into millimoles of HCl. See, 1 millimole of CaCO3, half of HCl. HCl is 2, half of 2 is 1, so that matches. So I get half into 25 into 0.75 millimoles. This is, these are the millimoles of calcium carbonate required, but they have asked me the mass. Now, molar mass of CaCO3 is most beautiful of all. It is 100 grams per mole. Nothing can be prettier. So, mass CaCO3 is moles of CaCO3 into molar mass, which is how much? How many moles? This ugly number. Now what this comes out to be? 0.75 is 0.25 into 3. 2.5 into 2.5. The square of 2.5 is 6.25. 6.25 into 3 by 2. This is what I obtain. I have no option but to multiply. This is 18.75 by 2, which is 9.375. Fine. 9.375. Now this gives me 9.375 millimoles into 100, which is 937.5 milligrams or 0.9375 grams. This, my dear, is the mass of calcium carbonate required. We have a question based on stoichiometry, and what does it say? Chlorine is prepared in the laboratory by treating MnO2 with aqueous HCl, and you are given a balanced reaction. That's very lovely. How many grams of HCl react with 5 grams of manganese dioxide? The first basic etiquette you should have is no stoichiometric calculations are done in grams, they are always done in moles. So you need to convert these grams to moles first. 5 grams of MnO2. Now molar mass of manganese dioxide, manganese is 55, oxygen is 32, that makes it 87. 87, heavy 87 is the mass of MnO2. So moles of MnO2 is 5 by 87 moles. Mass by molar mass, so many moles of manganese dioxide were given. 1 mole of manganese dioxide requires 4 moles of HCl by stoichiometric equation. You can see, if that is the case, then moles of HCl required is 4 into moles of MnO2 required, which is 4 into 5 by 87. Lovely, that is 20. by 87 moles of HCl is required. Are they asking me that? No, they are talking about mass. Therefore, mass of HCl is moles of HCl into molar mass of HCl, which is again very simple. How much is that? 20 by 87 multiplied by 36.5. Oh my God, as ugly as it gets. How much is that? Let's divide and see. I multiply 36 twos are, that is 73. So 730 by 87. God save me. How much is that? I'll say this is 870 minus something, right? By 87. Always try to convert numerator in terms of denominator, so it becomes simpler. 870, there is 140, I believe. Yeah. So that would make this 10 minus 140. Now 140 is 87. 87 twos are, no, forget twos are. 87, 90, 53. I'm just trying very hard, to calculate nicely. 87. Like this. Clean. 10 minus 1 would be 9. So this is 9 minus 53 by 87. Now let me try to settle this number 53 by 87 by trying to divide by something nice. The closest nice looking number I get is 17 threes are 51 and 17 fives is 85. Is that okay? Fine. So 53 by 87 is roughly 51 by 85, which is 17 threes are and 17 fives are, which is 0.6. So this number is close to 0.6. 9 minus 0.6 would be 8.4. Very close to 8.4. 8.4 grams of HCl would be required to react with this manganese dioxide.